But for now, because it is 10:30, I'm going to hand over to our next talker, who is Rory.
Hello, can you hear me okay?
Yes, yeah, you're all good.
Great. I'll just share my slides. Can you see those?
Yep, that is also perfect.
Okay, fantastic. All right, well, welcome everyone to my talk on generating agent-based models from scratch with genetic programming. So this is going to be presented by me, but it was co-authored by Jordi Arranz, who I think should be on the call as well. Okay, so what is this all about? The basic idea of this is, what if we could take ABM calibration, so calibrating the parameters of agent-based models, one step further. So we're not just looking at parameters, we're actually learning parts of the code of the model itself. And we're using genetic programming to do this, so we're learning the symbolic code. We show that this is a flexible approach. We're able to apply it to models in two different domains, which is opinion dynamics and flocking, so bird flocking. And the output of this process is basically interpretable symbolic code for the agent update functions of these agent-based models. So just as a quick refresher, what do I mean by ABM calibration? So traditionally, this means tuning the numerical kind of free parameters so that a model fits some observed data. So you can see here, maybe you have some real data. We want to twiddle with the parameters of these either manually or automatically so that the model output kind of more realistically tracks the real data. So this could be some sort of time series or a disease model or something like that. And what we're aiming to do here is say, go even beyond that. So even more flexibility. I guess one of the problems of this is like, maybe there are no parameter values where your model output actually fits your real data. So what if we can actually mutate or change the code of the model itself, so its actual logic? This is often called structural calibration. And what we're doing here is just learning the agent update function. So the logic for each individual agent. This slots into a kind of program skeleton, which loops over all agents. So we kind of know that we have some inductive bias here. We know that there are agents in this problem and they're doing something. We just don't know exactly what they're doing. So we'll just like learn that little bit that is their individual behavior. And so, yeah, what is genetic programming or program synthesis? I mean, genetic programming is just program synthesis using genetic algorithms. So this is kind of searching for a program which fits a given requirement. And typically we would use a domain-specific language, so a kind of constrained programming language. We can't use a general purpose language like Java or Python because it's just kind of too general, too large a search space and too flexible. So program synthesis is actually used in many areas. So Microsoft Excel is an example. If you do use flash fill, kind of drag over some data to induce equation, that's using program synthesis. And because we're basically learning a function to data here, there's a huge overlap with machine learning. You can see this, you can view this as machine learning. And yeah, like genetic programming is just doing this, but using genetic algorithms. So what are the challenges of this? It's hard to scale. It's a combinatorial search space. It's often a very sparse search space. There's another challenge with genetic programming called bloat, which means that you result in long, overcomplicated programs, which maybe detract from the fact that it's interpretable. But the benefits are that this, compared to techniques like neural networks, which really you're learning thousands of weights or millions of weights, not very interpretable, whereas this, you're kind of learning a concise symbolic program, which hopefully you can interpret. And we'll just show a few examples of that later on. So why are ABMs a good target for this? So it comes down to this idea of emergent complexity. You know, agent-based models can produce complex behavior when you're running with loads of agents, even just from simple rules at the agent level. And so what this means is you only need a few lines of code, you only need to learn a few lines of code in the agent update function, and hopefully you can still have this complex behavior at the macro level. And so this basically means we don't have to synthesize correspondingly long, complex programs, which would be a very difficult problem to get this complex behavior. So we're not the first people to apply genetic programming to agent-based models. So these are two examples in the literature, but there are more. And typically these start with an initial tentative model. So there's some domain knowledge encoded in the model already, and you're kind of mutating that, or you're recombining primitives from the domain. So, you know, you already have to know something about the domain or have some understanding, or start with an initial model that you then improve automatically. And what we're doing instead is kind of learning from scratch. And what we mean by this is starting from a completely empty program in that update function. And what this means is it requires less domain knowledge, like fewer priors. So maybe we can avoid some human preconceptions about the domain, or maybe we don't understand anything about the domain at all. Like maybe it's, you know, particularly in human behavior, often we don't really understand what people are doing. And so maybe this can give some surprising results that we wouldn't have come at if we just manually coded the model. We also used a larger, more flexible DSL, and we used it only doesn't really have any knowledge of the domain in this domain-specific language. It's just mathematical operators, basically. So this is a kind of larger, more flexible search space. And so the way I see this is a kind of spectrum of learning models. So on the far right-hand side, you've got kind of traditional agent-based modeling where you would hand code all your logic. On the far, and what we're doing is kind of pushing further left on the spectrum. I don't think we're all the way at the left, kind of completely learn from scratch. There's still some kind of priors in there. But yeah, as you go further to right, this is more domain knowledge is needed. And as you go further to the left, it becomes more flexible, but also makes it a much harder search problem. And so this was really inspired by a paper called AutoML0, which is actually nothing to do with agent-based models, but is a really ambitious application of genetic programming. So this is actually learning deep learning algorithms from scratch. So not just learning the weights of a neural network, but actually learning the code which trains a neural network from scratch using only basic mathematical operators as building blocks. And this is kind of really fascinating because it sort of rediscovers the concept of neural networks with two layers and the concepts of backpropagation and regularization and things like that. So it's really kind of learning all of that from scratch by itself. And so, yeah, when I read this paper, I thought, wow, yeah, maybe we could apply this. This is clearly a really ambitious application of this. Maybe this would work for agent-based models too. And again, just coming back to this point of a domain-specific language, we created one in Julia. And basically, this has a behavior, which is just a list of instructions. And this kind of represents the function, which is the agent update. So each instruction has a choice of mathematical operator. It has an output memory address. So there's kind of some memory registers that each of these instructions can write to, and then one or two input addresses. So that could be an input to the function or an existing memory address. And there was two experiments here, flocking and opinion dynamics. For flocking, we used a set of 23 vector operators. And for the opinion dynamics one, we used a set of 13 scalar operators. I'll show you what these are in the next slides. And there is some constraints to this DSL, so there's limited control flow. We have if conditions, so you can branch the program, but we don't have else conditions, and we don't have loops. So there is some branching, but it's still a bit restricted. And then there's a finite number of memory registers, and behaviors are kind of just interpreted line by line with Julia. It's not compiled ahead of time. And so here you can see the DSL operators. So again, the vector ones we use for the flocking experiment, scalar for the opinion dynamics experiment. And you can see these are based, there's nothing to do with like flocking in here. This is just like basic mathematical operations and some basic conditional operators. So I wouldn't worry too much about what these are, but yeah, basically these are just very kind of basic maths. And we use the genetic algorithm, obviously, to learn the code. So this is mutating these lines of instructions. This is called regularized evolution. This is basically just re-implemented from AutoML0. So it's a steady state algorithm, genetic algorithm. It's using tournament selection. So you basically take the best candidate from a random subset, mutate that and add it back to the pool. And then we do multiple pools so we can run them in parallel and also kind of preserve diversity as well. And interestingly, this is kind of linear genetic programming. So some approaches to genetic programming kind of use a graph structure to represent the program, whereas we're representing it as a linear kind of set of a list of instructions, basically. Now, so the mutation rules, because we're using linear genetic programming, they need to be aware of the search space. So you can't just randomly mutate the encoding. So there's 5 kind of things that we can do here. We can change an input, change an output. We can change one of the parameter values because each behavior comes with a set of numerical parameters. And I think you'll note that this means we're basically doing traditional ABM parameter calibration alongside doing this kind of structural calibration or learning the code as well. So this is like really flexible. And then we can add or remove an instruction, and it's biased towards removing more often than it adds. And this is just to try and keep the length down. And then we can also just randomize a whole chunk of instructions. And like I said, we start with 0 instructions and the algorithm has to add instructions in. So we're starting with an empty program or from scratch. And the loss function, so we didn't have real data on these domains, kind of flocking and opinion dynamics. So we basically generated some from a hand-coded reference model. So you could see this is trying to relearn the reference model just from the output data. And the loss function is just a mean squared error between these. And so we only run this reference model once, get a single trajectory, and we use that for the whole training run. So this is fairly data efficient. You're only really running the model once and getting that output. And we just turn this into data pairs. So this is basically just kind of supervised learning. It's data pairs for each agent and each time step. And this, just to summarize, is kind of a diagram of the training algorithm. So you can see here, we've got this reference model. We run a single trajectory, get the data. That's just used once in the loss function, or it's kind of used in the same data as using the loss function every time. And here we've got a population. We kind of select a behavior, mutate it, evaluate the loss function, and then add it back in, replacing the oldest one. So this is kind of, yeah, steady state. It's just constantly choosing one and then replacing the oldest. Okay, so this is a kind of experimental setup. So did this work? Like, what do the results look like? Let's have a look at that. So this is the first model we targeted, which is opinion dynamics. So we kind of hand-coded this model. This is just a really simple kind of threshold opinion dynamics model. This has basically, agents will randomly be selected to interact with each other if their opinion, they have a sort of value of opinion between 0 and 1. If the difference between their opinions, so you can see the pseudocode here, is less than a threshold, then their opinions move even closer. So this is a kind of idea of homophily, where you get closer to people you're already close to, and this sort of results in kind of polarization effects, which is what the model is exploring. So you can see this is the agent update function that we're learning. It's only 4 lines in pseudocode, but this is actually 11 instructions when encoded in the DSL, because you can only do one mathematical operation at once per line. So this would actually be several lines of like a multiply line, then a minus, and then a multiply. So that's just to say that this is still quite a challenging kind of program synthesis problem. Okay, so let's have a look at the results when we try to run the genetic algorithm in this. So you can see the loss here reduces quite nicely. There's some big jumps and gets down to a very low loss, which means it's recreated the target model very closely. Okay, so this is great. I mean, but it's kind of hard to interpret what this low loss means. So let's actually look at the output of running each model. So on the left here, you can see output from the reference model. So this is just all the opinions of the agents and how they change over the time steps. And you can see they form these nice clusters. And then on the right is the output from the synthesized or the learned behavior. And you can see these are basically identical. There are some very, very slight differences if you're paying attention, but if I remove these labels, it'd be hard to say, you know, which one is obviously generated and which one's hand-coded. So this clearly has learned the kind of logic of the model very closely. So yeah, so this is kind of clearly a good result here. And then let's look at the flocking model. So this was a simple Boyd's model of flocking. So each bird is only kind of following these 3 simple rules. So alignment, kind of align your velocity alongside your neighbors. Cohesion, kind of move towards the center of the group of neighbors. And separation, avoid colliding or getting too close to neighbors. So just with these 3 simple rules, based on local kind of perception, you get these kind of sophisticated, nice looking flocking patterns. Again, this is this idea of emergent complexity. And this a little bit different in this one is that we have some hard-coded logic in this agent update function. So we've got a spatial grid. So we have some hard-coded logic to update those spatial grids. That's basically a performance thing. Then we also have this move function, which is basically just physics. So take the newly calculated velocity and add it to position. And this is just saying that we kind of know how physics work. That's not really to do with flocking. It's just physics. We know how velocity works. So we can hand code this, and this just makes it slightly simpler target for we only need to care about learning the actual domain logic. So this steer behavior function has all of this is what we're synthesizing. We're starting from an empty function here. And this has all the logic to calculate the new velocity. So I would argue this is all the domain logic, kind of how agents perceive their neighbors and then update their new, calculate their new velocity. So this kind of takes in the center of mass of neighbors, the velocity of neighbors, and the agent's own velocity, and so on, and then calculates the new velocity. And so this is the bit we're synthesizing. And the results, again, we can see this reduces very nicely down to a low loss. There are a few big jumps, but I think we need to kind of compare the output to see what that looks like rather than just knowing this loss. And this is kind of some plots I made to, again, show this, the reference behaviors on the left and the learn behaviors on the right. So this is kind of just showing the movement of flocking, but in a static image. So we can see trails of birds. And again, these are not identical because it's a chaotic model, but they're very similar kind of in terms of just subjectively. So, you know, we can see there's this kind of curved movement. There's like different clusters which are replicated. There's kind of birds flying off in certain directions. And so you can see, even though these aren't identical, they're subjectively very similar. And maybe this is even clearer if I show this video. So again, this is reference model on the left-hand side and synthesized one on the right. This is kind of, again, not identical. It diverges slightly, but you can see, you know, this is very similar movement. You can, I think, be satisfied that this is subjectively or kind of recreated the flocking behavior that we care about. We don't care about it recreating it exactly, but it's kind of showing these flocking patterns in a similar way. And again, if I remove these labels, it'd be hard to say, okay, which one's obviously synthesized or not. And I guess I will come back to the point of generalization. So I think we obviously just trained this with a single trajectory, but it's worth noting here, this is actually running with far more agents than it ever saw in the training run. So I think it was trained with about 600 agents, and this is about 1,600. So you can see it already generalizes to larger numbers of agents and sort of outside of this training distribution, but we did some more quantitative experiments on that later. And again, here you can just see how this evolves over time. So it starts off, this is kind of showing as the training run progresses, you know, every so many steps, we kind of visualize the output. So it starts off, they just kind of fly off in different directions. And towards the end, you can start to see these kind of flocking patterns emerge, where it's more kind of clustering and kind of turning around. Okay. So that was the output for the models, but you know, one of the claims here is that this can generate interpretable code. So let's have a look at some of the output code itself that's being learned. So what I'll say first is, for both of these examples, I've taken the raw generated code and kind of made it a bit more readable. I've combined different instructions on the same line, and I've also given some kind of human readable names where I could pick out specific kind of concepts. So this is me going through interpreting a bit, but this is kind of functionally and logically equivalent to the original raw generated code. I've just like combined some lines and made it a bit more readable. So this is a generated code from Opinion Dynamics. Okay, there's quite a lot going on here, but we can look at the pseudocode again, and we can see the kind of core bits of this logic are we're getting the difference between opinions, doing some sort of conditional logic on that, and then updating the opinions. And you can see this here in the generated code. So the first thing it does is get this delta opinion, so find the difference between the two opinions. Then there's some conditional logic between, okay, something, and then we're updating the parameters if this condition is true. This condition happens to be if this temp B thing is approximately equal to 0. So that's a bit weird. When I first saw this, I was like, you know, this is a bit strange. What's going on here? I kind of looked into this. It turns out temp B is actually a polynomial function of this delta opinion, which you can see plotted here. And basically, yeah, when this polynomial is plotted is less than 0, this is equivalent to this approximate, this condition here. We can see, so basically temp B is between minus 0.2 and 0.2. Then we do this function, which basically updates the opinion as equivalent to that. And it turns out the value for D that I used in the original reference model was 0.2. So this is like recreating this logic exactly with the same value. It's just doing it in a bit of a roundabout way. It's kind of like, yeah, sort of bizarre but ingenious way of doing this. It's kind of like, you know, doing this interpreting was sort of like reviewing the code of a colleague who was a genius but also totally insane or something like that. So yeah, this is quite interesting that we can kind of figure out what's going on here. And again, for the flocking, in some ways, is much easier to read. So this is the original reference model that I wrote, and then this is the simplified version of the raw code. So again, I basically just combined a few lines and given human readable names, but it was easy for me to pick out these concepts that are the same from the original model. So you can see we have separation, alignment, cohesion. In fact, these last two lines are basically identical. And again, you can see we're, like I said before, we're like learning the parameter values alongside the code. So we've got this params 8, which is 4.9987, very, very close to 5.0. So again, this is what you would expect given that the results are very similar, but it's good to know that, you know, this has learned the model effectively quite similarly. So again, I mentioned a bit about generalization. So this is a kind of whole loss plot. We did an experiment where, okay, so in the training run, we only showed it one data set. So this data set, the loss for this data set is marked as red here, a red dot. So we generated lots of other data sets using different random seeds and then calculated the loss for all of them. So And it turns out, you know, the loss for all of these different data sets, which are outside what it saw for training, are still very low and still very close to the, you know, the red dot. So yeah, we can see, especially in the context of all this loss, that this is generalized very well and that it gets a low loss even for data sets it hasn't seen. And, you know, this was similar, possibly even better in the case of flocking. This is like the red dot again, and this is a distribution of loss values for other kind of test data sets. All right, so just to kind of sum up and discuss a bit about this. So what are the limitations of this? Again, the DSL is still kind of restricted. There are no loops. I mean, this was done for very good reason, particularly because as soon as you have loops, then you don't know how long your program's going to execute. So, you know, we could kind of try this with a less restrictive DSL or kind of even larger set of operators. So all the agents are homogeneous, like they're all learning the same function. So it would be very interesting to try this with like multiple different types of agents, or some possibility that agents would have different. I mean, they could, in theory, learn sort of conditional logic that would make agent behavior quite different depending on certain values. But again, and these are obviously quite simple models. This was a very, very simple opinion dynamics threshold model and a simple flocking model. So I think the question here is like, we'd really love to try it on some more complex models. And what would we like to do in future? So I think trying this with real world data, obviously we're just relearning kind of hand-coded models here. But in theory, you know, all they're seeing about those models is the output data, the kind of state of the agents. So we could just shove in some, if we had the right data sets, we could just use some real world observed data sets in different domains. And again, this is flexible. We kind of shown that it works in different domains. So in theory, you should be able to take any data set and learn something at least. And then another idea is multi-objective optimization. So we're kind of learning based on approximating or sort of targeting the fitness. But another factor here is we could try and make sure that the programs are more interpretable by reducing their length or some other objective that's related to the complexity of the learned program. So we could try multi-objective optimization for that. And then another kind of interesting idea is, obviously I went through this method of interpreting the raw code and simplifying it, but maybe some of that itself could be automated. So Julia in particular has libraries for algebraic manipulation of Julia code, so you can kind of simplify mathematical expressions and find equivalent ones. So maybe we could do this. There's also things like decompilation tools, which will like simplify and apply variable names and things like that. So not only could we do this to make the code more readable, we could do this within the training loop. So we could say kind of learn for a while and then simplify the code, or like simplify algebraically and then keep learning. And maybe that would like learn more condensed or generalizable kind of concise programs. And yeah, just to sum up here, so we've successfully synthesized the logic for simple agent-based models with genetic programming in 2 different domains, opinion dynamics and flocking. We've shown that agent logic can be learned from scratch. So we're going more to the left on that spectrum, away from having to manually code things. This makes it a lot more flexible. And we've done this with a flexible set of DSL operators. So in the DSL, it's just kind of simple arithmetic and maths and conditions. It's nothing to do with flocking and opinion dynamics. So we've kind of learned this out of things which have no knowledge of the domain, I guess. And we've got a high performance implementation of Julia. And again, the performance, this is one of the reasons we chose Julia for performance. The performance was really critical here. So if you notice the x-axis on the graphs, it takes tens of millions of kind of mutations or loss function evaluations to be able to learn these. So it's critical that that can be done really quickly. And yeah, basically that's it. So thanks very much for listening. And yeah, I think hopefully we have some time for questions.
Yes, you do have some time for questions. Well done. What a very interesting talk. And we've already got some questions for you written in the Q&A. In fact, we've got a lot of questions. I hope there's going to be enough time to go through all of them. But if not, you can reply on the chat. So the first question is from Oscar. He says, very interesting. Do you have some constraints on the memory OPS and the space the agents can work with?
Yep, so I'm not sure exactly what you mean by OPS. Is that just like memory ops? But so yeah, certainly there's a limited number of memory registers. I mean, these are all things that have to be configured when you set up the training run. So we decide a number of memory registers that we're going to allow. And then also we set a limit on the kind of program length as well that it can't go beyond. So yeah, and these are kind of, I guess, maybe a bit problem specific. You can kind of make an informed choice about that, how much kind of working memory or registers that they have. Hopefully that answers it.
Okay. If it doesn't, Oscar, you can always raise your hand and then I can unmute you and you can have a bit more of a discussion. But hopefully it has answered it, and I will go on to the next question, which is from Lana. She says, can you apply/find unexpected variations after you found the original model?
Yeah, so this is a good question. If I'm understanding it correctly, I guess that there could be some kind of new behavior that generates. I think maybe the current setup we have here is less well set up for finding kind of new variations, because I think it's kind of targeting relearning the original model. So maybe it's less sort of open-ended. So it depends what you mean by kind of unexpected variations. But certainly the idea is if we were learning this from real data, hopefully this might find some unexpected way or function to fit the real data. And maybe that would be different from what we'd hand coded. And then obviously we just have the code, we could slot that into another model or kind of tweak it or just take out a bit and put it into another model.
Okay, and then I think we've got time for one more question, but there are still loads in the chat. So Rory, you might have to spend a little time after the talk going through. It's what happens when your talk is so interesting. It's a curse. So the last question is, can this approach help us to synthesize our models to make them lighter or even completely automate the modeling process?
Yeah, so this is a great question as well, because I tend to focus on learning from real data, but actually this idea of relearning existing models, like maybe you have a model that's really slow to run, or maybe there's some other kind of features of it that you want to learn a different type of model. So maybe you want to learn a model that's entirely differentiable or something like that. And I think the idea here is, yeah, there's some really interesting applications by relearning existing models. And wait, yeah, sorry, what was the second part of the question? Oh yeah, kind of could this be used to automate modeling? And I think, yeah, I guess this is in part why we're interested in it in the long-term view. I mean, we're a tech company, and I think the idea would be if we can give people tools to do modeling at a sort of higher level of abstraction or automate some of that bits of just, it's basically like automatically evaluating different hypotheses for data in a very kind of automated way. So that really is the kind of long-term way that we're thinking about it. Not that we want to put any modelers out of a job, but I think it's just about giving people extra tools, right?
Okay, fantastic. Thank you so much, Rory. If people do still have questions for Rory, he's going to stay on as a panelist. So if you keep typing in the Q&A, then he'll be able to see them and he'll just answer them like privately via text. But of course, I'm sure you can get him via Slack as well if you're watching this as a pre-recorded talk.